Another player in all this is Einstein. Now, Einstein is one of the most famous scientists of all time, and he did a lot of work with relativity, both general relativity and special relativity. But what he actually received the Nobel Prize for is what's called the photoelectric effect, and that's what we're going to talk about right now. Now, the photoelectric effect is a fascinating phenomena where you can shine light on a metal surface, and all of a sudden, electrons start pumping out of the metal. And that's amazing because you wouldn't think that light would do anything. Like if you are under a lamp or something, maybe you'll feel a little bit warm, but you don't feel your body breaking down or something. Well, with metals, you can actually have electrons kind of kicking it out. They actually start moving around. And if you have moving electrons, you can measure them voltages and stuff like that. You stop the light, you stop the electrons from moving. So light is actually making electrons move. And this is really fascinating because you wouldn't think that light would be able to do that.
When yellow light shines on the metal surface, electrons are knocked out of the metal. As long as light of sufficient frequency shines on the metal, free electrons are produced and a current flows through the tube, as measured by an ammeter. The current stops flowing when the light is turned off.
It's a fascinating phenomenon, and it shows that maybe light is doing more than you might think. It's not just warming something up. This photoelectric effect is fascinating. It really, what it does is it shows how light can behave as a particle. Now, just kind of step back from that for a second. If I threw a baseball to you, you could catch it, and you could throw the baseball back to me, and that would be particle behavior. But if I shined a light at you, you wouldn't think you could catch the light, and you couldn't throw the light back at me because light is light, all right? Well, light here is behaving as a particle because it's like basically banging into that metal and electrons are kicked out. And if I threw something hard enough at a wall, the wall would break up or something. That's kind of like what light is doing. It's acting like a particle, which is really wild. And this, again, blew scientists' mind. Now, classical physics predicted that the energy of the electrons that are kicked out should increase as the light intensity increases, but that wasn't seen. It's just one type of energy that comes out. And you do have to have a minimum energy or minimum frequency for this to happen. So this is the first time that we've seen what's called the wave-particle duality of light. It's light behaving as both a wave, which is what we're used to, or as a particle. So in the photoelectric effect, you're actually seeing light as a particle, which is different than if you have light as a wave. So pretty cool kind of stuff we're getting into here. And that's why, again, Lord Kelvin's cloud speech is just silly. So if light consists of particles like quanta, like Planck predicted, this makes this all understandable. And the particles can be thought of as little pieces, which are now called photons. So a photon, when we talk about it, is just going to be like a small piece of light. And it's not that you can like separate one photon from the other, but light can be thought of as having these little tiny photons with discrete energy. So we can calculate the energy of one photon as well as a mole of photons for our red light that we talked about earlier. Now, earlier we saw red light with our wavelength of 700 nanometers had a frequency of 4.28 times 10 to the 14th hertz, or 4.28 times 10 to the 14th inverse seconds. We're going to use this on the next slide then to find first the energy of one photon and then the energy of a mole of photons. From earlier, the wavelength at 700 nanometers had that frequency, 4.28 times 10 to the 14th hertz, or inverse seconds. Now, the energy per photon is h times nu. H is Planck's constant, 6.626 times 10 to the minus 34 joule seconds, and the frequency we're using here, 4.28 times 10 to the 14th hertz. So when you multiply those together, notice here how we have the inverse seconds, which is like 1 over seconds, and here we have seconds. So the seconds and the inverse seconds cancel out, and the units that are left are joules, 2.84 times 10 to the minus 19th joules. And joules is what scientists use most of the time for energy. So that's an energy per photon. Every time you see joules, think energy. And 10 to the minus 19th joules is not a very big number, definitely. So there's not a lot of energy per photon. However, a lot of times what happens is people will think about that in terms of energy per mole of photons. So the joules per photon number that we calculated earlier, you can multiply by Avogadro's number, 6.022 times 10 to the 23rd. Now, we talked about it as atoms per mole and molecules per mole in the last chapter. Here we're talking about it as photons per mole. So you can see the versatility. This is why they call it the chemist's dozen, et cetera, et cetera. Anyway, you get just a massive number of joules per mole. And most of the time what people will do is they'll divide by 1,000. A kilo is 10 to the third. So a kilojoule or kilojoule is 1,000 joules. And you end up with 171 kilojoules per mole. Now, this is a bigger number, obviously, than the joules per photon. But what's really cool is we're going to see in Chemistry 222, that's the energy that you can actually use to break chemical bonds. And so there's a field of chemistry called photochemistry, where literally they just shine light on a chemical reaction, and the chemicals start reacting because the bonds are broken through the light. Amazing field. Very, very cool. I was always jealous because these people would turn the light on their chemicals and leave for the weekend, come back on Monday. They'd have their almost 100% yields. We'll talk about what that means. There weren't any bad products. Fascinating field. But regardless, nothing neither here nor there, light can be used to enact chemical change, which is just fantastic. And that's one of the advantages of knowing about the photoelectric effect and Planck's constant, stuff like that.